Okay, let's go ahead and get started. Exponential functions. So I'm hoping a lot of the things we're going to talk about today will be repeated for you. So we usually talk about exponential functions right after polynomial functions. Remember, a polynomial is a number times a variable to a power, plus or minus a number times a variable to a power. The difference between that and an exponential function is now, instead of our variable being to a power that is known, it's flipped. The base is what we're going to know, and the variable will be in the exponent. So that's what makes it exponential. So something like this is the basic form of an exponential function. F of x equals a to the x power. We call a the base. There's a couple of restrictions on a. A must be a positive number to meet our exponential guidelines, and it cannot equal 1. Because if it was 1, 1 to any power is 1, and it would just look like a straight line. It would not be an exponential curve. Okay. Because the base is a can be decimals, positives. The domain, what we're plugging in, can be all real numbers, meaning my exponent can be positive, can be negative, can be 0, anything like that. So we're not going to worry about any domain restrictions when we see these as well. Okay. Nothing that I can't, no power that I can't take a positive number to. All right, so first few problems are going to be pretty straightforward. They're going to be evaluating, plugging the number into the exponent, and simplifying, which is what we're ultimately going to do with a table of values to be able to graph these. So first one, f of x equals 2 to the x minus 5. We're evaluating f of 4, which means we're just going to take 4, and we're frozen. Tally it. We're tallying. We're going to call data collection. That's what we do in math. Yep. Did it freeze up here? Oh, it's definitely come on. So 2 to the 4 minus 5 power, when I plug it in, will look like, what will the exponent simplify to be? It'll be 2 to the negative first. Do you remember how to work with negative exponents? You never? Okay, so if you have a negative exponent, you can move it from the numerator to the denominator or the denominator to the numerator to make it a positive exponent. So in this case, think of it as 2 to the negative first over 1. If I put it in the denominator, it becomes a positive 1. And then 2 to the first, of course, is just 2. So it simplifies to 1/2. Okay, next one, I have negative 3 times 10 to the x power, and we're evaluating it for f of negative 2. Negative 3 times 10 to the x for f of negative 2. So we're just going to plug in that negative 2. Negative 3 times 10 to the negative second equals, what's 10 to the negative second? The same as. Right, so think of it as 1 over 10 squared. Or if you want to do that all in one step, 10 squared gives me 100. And then negative 3 times 100 is negative 3 100ths, or if you say 0.03, negative 0.03, that's fine as well. It's an exact decimal there. Okay, 1/7 to the x power is the next one, and we are evaluating it for 1/3. Okay, f of 1/3. So that's going to look like 1/7 to the 1/3 power. When you have a fraction taken to a power, you can distribute that power to both the numerator and denominator. So it would be 1 to the 1/3 over 7 to the 1/3. 1 to any power is what? 1. Do you know what 1/3 power is the same as? It's the same as a cube root. Yeah. So you can type it in your calculator like this, 7 to the 1/3, or you could just say cube root of 7. Either way, that's not going to be a nice, pretty number. So I'm just going to write cube root of 7. And I'm going to leave it down there. Okay. Again, Math Excel, you might have to approximate it. You can always type that in your calculator. And I like the 1/3 power. If you want to find the cube root, it's under the math menu in your calculator. Maybe like 4. Okay. The square root should be in there, maybe 2. And then there's also an x root. If you want to do like a 4th root or a 5th root or something like that, that's all in the math menu. Okay, and then the last one, I have 4 to the x power. Make it a little bigger here, maybe. And we're evaluating it for -3/2. So it's going to look like 4 to the -3/2 power. This one you actually can do in your head. If you have a fraction exponent, you can split it. 3/2 is the same as 1/2 times 3, and you can make either of them negative. Let's say I want to make the 3 negative. This is one of your power properties of exponents. If they're separated by parentheses, you can multiply them together. So -3 times 1/2 would take me right back to that -3/2. Anything to the 1/2 power is the same as doing what? I just kind of talked about that a second ago. Square root, square root. So square root of 4 is 2. So now I have 2 to the -3rd power. And then we can simplify that. What do? Put in the denominator with the 3rd power, and 2 to the 3rd is 8. Okay. Of course, you can just type these in your calculator to get exact answers as well, but it's a nice little review of your exponent properties also. Okay. For right now, we're not going to. Technically, yes, but no. We're not going to do that. Okay. All right. Next up. Oh, go ahead. Question.
So, say it was 4 to the -8. I would just do 4, 1/2, and then negative the answer. That can work with like thirds, fifths, 27s, 63rds.
All those. All good. Okay. Next up. Graphing an exponential function. So we're going to try to do this by hand without a calculator. Of course, you can always use your calculator to check it. Remember, what's the domain of these? All real numbers. You can plug in any numbers you want. So again, a good. Oh, we're closing again. No, we're not. We're good. Plug in any numbers you want. I'm going to use -2 because it gives me some negatives, positives, nice pretty numbers to work with. You should be able to do this in your head. 2 to the -2nd power will be what? 1/4. 1 over 2 squared. 2 to the -1st. 1/2. 2 to the 0. Anything to the 0 power is what? 1. Anything to the 0 power is 1. 2 to the 1st. 2 and 2 squared. 4. Okay. So let me go ahead and plot these. At -2, I'm at 4. At -1.5. 0, 1, 1, 2, 2, 4. So we get this kind of curve shape. We call it an exponential curve. Do you remember what kind of property is going to show up when I connect the dots here? What we're going to have on this graph? I don't know if we talked about these when we did our basic functions in chapter 2. The line that we're going to get close to but not touch. We're going to have an asymptote. Where's the asymptote going to be at? It's at 0. Yeah, you're going to have a horizontal asymptote at 0 here. And that's because no matter what I plug in for a variable exponent, there's no way I can get 0 out, and there's no way I can get a negative number out of this because that base is a positive number. So even if you plug in very tiny decimals, you're going to just get a very tiny positive number. We're going to get very close to 0 but not touch it. So just make sure you don't cross that. So if I wanted to name properties of this real quick, my domain is what? All real numbers. My range would be what? 0 to infinity. Asymptote. Make sure you write the equation. Either y equals 0, or you could say the x-axis. And then, can you tell me, is this growth or decay? This is growth because it's increasing from left to right. It's increasing over all the numbers, actually. And again, we call this an exponential curve is the shape we're seeing here. Okay, I'll give you a couple minutes. You guys try the next one. Graph f of x equals 2/3 to the x. Try to get exact numbers in your table if you can. Plot the points, name the properties. Okay. maybe on this one. Okay. So I use -2 to 2 again. 9/4, 3/2, 1, 2/3, 4/9. Sketch should look something like that. This is an example of decay because it is decreasing from left to right. Your properties are all the same. Domain is all real, range is 0 to infinity, and you have an asymptote at either the x-axis or y equals 0. Any questions? No? Okay, so next slide is kind of a summary of our growth versus our decay functions. So now we're talking about, let's say I have a base, they're using a b here instead of an a, and then we have an a value out front. This is typically how you'll see an exponential function written, probably what you're more familiar with from Algebra 2 would be my guess. The a value represents an initial amount, typically, especially if we're talking about word problems, things like that, initial value. It's also going to be, notice what we see on our y-axis. It's going to be our y-intercept. B is considered our growth rate. If B is a value larger than 1, we see exponential growth, like we saw in that first graph. If B is between 0 and 1, which remember it can't equal 1, and it can't be negative, can't be 0, then we see exponential decay. So those are the two possibilities. Yes? We are not going to do logistic growth. No. We could. It's in our book, but we don't do it. Huh? AP by. All right. So what we're going to do at the bottom real quick, we're going to add the properties on kind of like we did with our basic functions in 2.6. So this is one that we had skipped over. So what is the domain of both of these? All reals. So nothing that's going to change there. We're going to put negative infinity to positive infinity. And that's actually part of our definition of an exponential function. Domain is always all reals. The range will both be 0 to infinity. Asymptote, y equals 0, or you can say x-axis. Intercepts. Let's start with a y-intercept. You have a y-intercept where? Not at 0. At A. Whatever that happens to be, our initial amount or starting value for both of them. X-intercepts. Do we have x-intercepts? Does it touch the x-axis? No, we just said there's an asymptote there, right? So none. Okay, what about even, odd, or neither? So even is symmetric to the y-axis. Odd is symmetry to the origin, flip it upside down, looks the same. And then neither is neither. This is a neither. Yeah. If you flip it upside down, you're going to see the graph is completely crumpled. So neither. And then end behavior. We need to talk about these. How many ends do these graphs have? They have 2. Okay, so we're going to write it twice, and we're going to use the limit notation. So starting with exponential growth, because this is the big difference between the two. I'm going to squeeze it in there at the bottom. I'm going to list it actually on the graph here. Okay, so starting with exponential growth. Limit as x approaches negative infinity. On the left, I agree. F of x equals. So on the left, what is this graph approaching? 0. It is getting close to the asymptote. Yes? That's the notation you're going to see in calculus. So we're just getting used to it. Okay, and then what about the other limit? X, if you have an arrow on the test, that's okay. I won't mark it wrong. But we're going to use equals here now. Okay. And then what's the other one? X approaches positive infinity. So as it goes to the right, f of x approaches, that's going to go up forever. So infinity. Okay. So now decay, you're going to see is just the opposite. X approaches negative infinity. F of x equals what? On the left, that graph goes up, infinity. And on the right, it gets close to my asymptote at 0. Okay. That's really the only difference in the end behavior. Increasing versus decreasing. Any questions? Growth and decay. Okay, if you're not sure if you have them, you can always graph, but usually that growth factor, that B value, is going to be the easiest way to tell. Number bigger than 1, it's going to grow. Between 0 and 1, it's going to decay. All right, so let's try this problem. You're going to see one like this on Math Excel. Find a function, and it is of the form c times a to the x that contains the following points. So we've done this with lines, we've done this with quadratics. Now let's do it with exponential functions. Given a couple points, find the key parts of the equation and finish the function. All right, so remember, C and A are what we're solving for here in this case. Any variable other than X and a Y we want to find a value for. Exponential functions are curves. So do they have a slope? No, slope is only what? A linear function. Okay, so all we can do at this point is plug the points in and see what happens. Okay, I plug in 1, 1. I have 1. We're going to plug in 1, 1. 1 equals C times A to the first. A to the first is what? A. So I have 1 equals C times A. I still have 2 variables there, nothing I can solve for. Okay, so I'm going to leave it. I'm going to go to the other one. Plug in 2 and 1/5. So 1/5 is my Y. C times A. And again, I still have 2 variables, nothing I can simplify at this point. So I have 2 equations that contain the same 2 variables. What is that called? Starts with an S. System. It is a system of equations. So 2 ways you can solve this: elimination, which is really the only something we do with linear equations most of the time, or substitution. And we've done it with before. If you remember, there was like a perimeter area problem with quadratics, where we had 2 different equations. We got a variable alone in one equation, and we plugged it into the other. That's the idea here. Okay, I'm going to take the left equation. You guys want to get the C or the A alone? It doesn't matter. C. Okay, if I get the C alone, it's C equals.
Oh, that's not 3.5.
3.5. All right. C equals 1 over A. Okay, so C is equal to 1 over A, which means I can go to the other equation and replace C with 1 over A. So 1/5 equals 1 over A times A squared. What is 1 over A times A squared? A squared over A, right, which reduces to A. So 1/5 is A. What do I still need? C. So you can go back to the other equation if you want. I have 1 over 1/5, which dividing by a fifth is the same as multiplying by 5. Or you can always type that in your calculator and you'll see that C equals 5. So what's my final answer? F of X equals 5 times 1/5 to the X power. And you can't simplify any more than that because the 1/5 is to the power and the 5 is not. Okay, we don't have the same bases there. All right. So you guys try this one. Now this one, the exponential function is a little bit different form. A to the X plus B. So you're using these 2 points to solve for A and B. Once you have your final function, then evaluate F of 4. I'll give you a couple minutes. I plugged in 0 through the start. Remember, anything to the 0 power is 1. Subtract 1, you get B is 2. Okay. Then I put that in for B, and I use my other point. So Y was 6, X is -2, and subtract the 2, I get a 4. A to the negative second is the same as 1 over a squared. And then you can think of this like a proportion, cross multiply if you want, or just multiply by the denominator on both sides. You know, with 4a squared equals 1, divide by 4, take the square root. It can't be a negative in half because the base, it is the base of our exponent. The base of our exponent must be a positive number. So it's just positive half is the only option. So a is a half, b is 2, plug in 4, you get 1/16 of u, which is 33.
Yeah.
Okay. So sometimes you don't have to use the system. Of course, you probably could if you got stuff. I always try to look for any points that contain a 1 or a 0 though, because we have some nice exponent properties that go along with those. It makes the problem a little bit easier. I start with those.
So once you got it,
Yep. Just like when we had lines, we were solving for y equals mx plus b. We found m, we found b, we wrote our equation by filling them in. So, same idea. Okay? Okay, so last couple slides talk about, let's say you have now transformations on your basic exponential function. Okay, so transformations that we talked about before, shifting, left, right, up, down, reflecting, stretching, all of those wonderful things. Okay, so this is an example of a transformed exponential function. The original exponential function that you would be comparing it to is, let's say, it's f of x equals 3 to the x. And the base of 3 is something that is the same, but then we don't have anything else weird happening with powers or numbers out front, anything like that. As far as graphing these go, if you're doing them on Math Excel, you'll probably have to graph using the transformations like you've done before, where you're listing the vertical shift or the horizontal stretch, things like that, in the proper order. Remember, the order to those was as they affect the x. Okay, so left and right was first, then our vertical and our horizontal stretches and shrinks were second, then our reflections, and then finally the shifts up and down where we added on. So if you want to do this on Math Excel, you would have to do linear transformations. What does the +1 in that exponent do, do you think? Yeah, think about that as being inside the function here. Okay, it's inside our exponent, an exponential function. So it's left 1. Okay, another person. Left 1. Okay, what do you think the 2 out front does? Vertical stretch. Good. Remember, multiplied on the outside. Vertical stretch, you could say by a factor of 2. And then what does the -1 do? Down 1. Okay, so one way to do this now is you can graph 3 to the x power very easily, and then you could perform these transformations. And you would actually do them in this order. You move everything left 1, do a vertical stretch, so up and down by a factor of 2, you would double it, and then you move every point down 1. Honestly, though, if I were going to graph these, I'd probably just make an XY table and plot the points. You will see, though, because we're shifting and moving around, the curve shape could look a little bit different. It might increase versus decrease, or our horizontal asymptote might be located in a different place. So you can pick any points you want. I would start with -2 to 2, and then if you feel like that doesn't give you a good enough set of points, you can always make this table larger. You can plug them in very quickly. If I plug in -2, -2 plus 1 would be a negative first power. 3 to the negative first is a third. Times 2 is 2/3. -1 would be -1/3. Okay. If I plugged in -1, that would be a 0 power. 3 to the 0 is 1. Times 2 is 2. -1, 1. If I plug in 0, I would have 3 to the first. 3 times 2 is 6. -1 is 5. If I plug in 1, I would have 3 squared, which is 9. Times 2 is 18. -1 is 17. And we can see this is going in the wrong direction right now. So I'm not going to plug in 2. I'm going to plug in -3 instead. So I'm going to go way off my graph. If I plug in -3, -3 plus 1 is -2. What's 3 to the negative second power?
That's 1 over
9. Times 2 is 2/9. -1 is -7/9. Okay, and again, a basic calculator to help you get those. All right, let's plot the points. -2, I'm at -1/3. -1, I'm at 1. 0, I'm at 5. That's my intercept. 1, I'm at 17. That's way off the graph. And -3, I am at -7/9. Make sure before you connect these points that you know where the horizontal asymptote is. Look at the values in my table. If I continue to the left, -4, -5, -6, etc., what am I approaching? -1. And that up-down shift can help you. We moved the whole graph down 1, right? So doesn't it make sense that our horizontal asymptote would move down 1 unit? Okay, so let me connect to that. And then we name the properties very quickly. So domain is always all the numbers. Range now is what?
Range is
-1 to infinity this time. And then I have a horizontal asymptote at y equals -1, which again, you can find that in your transformations, or you can find that on the graph itself as your values approach a certain number to the left or to the right. Okay? Yeah? You would have a negative. So you would have a negative like in front of the 2, for example, that would be a reflection over the x-axis. You would have a negative, it would be in the power in front of the x. Yep. Just like we talked, anything inside those brackets, when you look back at that chart we had before, that would happen in these problems in the exponent. So the b and the c and the reflection of the y. Okay, so we will finish this lesson tomorrow. I will do the self-find model for you.